If an aircraft were to be flying, but producing no lift or downforce, the only drag present would be parasite drag, which, as already seen in the drag family tree, is comprised of skin friction, form, and interference drag. An aircraft's skin, regardless of material, will to some degree have imperfections or roughness in its surface, due to paint, rivets, and other protrusions, contamination, etc. Air particles in direct contact with the surface are accelerated to the speed of the aircraft and are carried along with it. Adjacent particles will be accelerated by contact with the lower particles, but their velocity will be less, but only slightly so, because of the low viscosity of the air. As distance from the surface increases, less and less acceleration of the air takes place. Thus, there exists over the entire surface a layer of air whose relative velocity ranges from 0 at the surface to a maximum at the boundary of the air that is affected by the passage of the aircraft. This layer, from the surface to the point where there is no detectable viscous effect, is known as the boundary layer. Where the change of speed is smooth and progressive, the flow is referred to as laminar. In flight, the nature of the boundary layer will determine the maximum lift coefficient, the stalling characteristics, the value of form drag, and, to some extent, the high-speed properties of the aircraft. The boundary layer is not always smooth or laminar. In general, the flow over the front of a surface will be laminar, but will become turbulent some distance back, at a point known as the transition point. The increased rate of change of velocity at the surface in turbulent flow will give more skin friction than laminar flow. A turbulent boundary layer also has more kinetic energy than a laminar layer, and is more resistant to separation. A forward movement of the transition point will increase skin friction because of the greater area of turbulent flow. There are two factors that can affect the position of the transition point. First, the surface condition. The thin laminar layer is very sensitive to any irregularities. Roughness on the leading edge skin can cause early transition to turbulent flow, which fans out downstream, causing a marked increase in skin friction drag. Secondly, a laminar layer cannot exist where pressure is rising in the direction of flow. Over a curved surface, like a wing, the transition point is at or near the point of maximum thickness, which is the point of lowest pressure. So the flow is against what is called an adverse pressure gradient. The transition point is thus further forward than if the surface were flat. It is worth noting that for clarity, the depth of the layers has been exaggerated in the diagrams. In reality, the laminar boundary layer is about 2 mm deep and thickens to about 20 mm in the turbulent flow. Form drag results from the pressure at the leading edge of a body being greater than at the trailing edge, hence its alternative name. Overall, skin friction causes a continual reduction of boundary layer kinetic energy as flow continues back along the surface. The adverse pressure gradient aft of the transition point also causes a further drop in kinetic energy. If there is insufficient kinetic energy to overcome the adverse pressure gradient, the lower levels of the boundary layer stagnate, and the upper levels overrun them, causing separation. The surface flow after the separation point will now be forwards, but because of separation, there will be a lower pressure at the trailing edge than at the leading edge. The aerodynamic force from high to low pressure thus acts against the direction of flight as form or pressure drag. The loss of the kinetic energy required to overcome the adverse pressure gradient and prevent separation of the boundary layer can be caused by various factors. As angle of attack increases, the transition point moves closer to the leading edge, and the adverse pressure gradient becomes stronger. This moves the separation point forward. Eventually, the separation point is so close to the leading edge that there is not enough wing area to generate the lift required. The CL decreases rapidly, and the wing stalls. Another factor concerns transonic flight. When a shock wave forms on the upper surface, the increase of static pressure through the shock wave creates an extreme adverse pressure gradient. If the shock wave is strong enough, separation will occur immediately behind it. This phenomenon will be explained more fully in the part of the syllabus on high-speed flight. Coming back to subsonic flight, a turbulent boundary layer will resist separation better than a laminar flow meeting the same adverse pressure gradient. In some circumstances, this is an advantage. For example, some aircraft have small vanes called vortex generators, fitted on top of the wing ahead of the ailerons, to ensure that the boundary layer remains attached longer than on the rest of the wing, to retain control effectiveness at speeds close to the stall. In normal flight, however, laminar flow is preferable, owing to its lower drag penalty. The term streamlining is often used to refer to the smoothing of a vehicle's or aircraft's design shape, or the addition of fairings or fillets to modify it. But more specifically, it is the shaping of a body to keep separation as close to the trailing edge as possible. Streamlining increases the ratio between the length and depth of a body, reducing the curvature which induces an adverse pressure gradient. The best fineness ratio, as it is known, has been found to be 3:1. The combination of form drag and skin friction is known as profile drag, as it can be considered that it results from the cross-sectional area or profile of the aircraft presented to the relative airflow. The final element of parasite drag is interference drag. When considering a complete aircraft, the parasite drag in total will be greater than the sum of its parts. This additional drag is the result of interaction between the boundary layers of adjacent parts of the aircraft. Probably the best example of this is the junction between fuselage and wing at the wing root. The air is accelerated over the wing and will be faster than the airflow over the fuselage. Where the two flows mix in the angle between the two surfaces, the interference causes turbulence and drag. The solution to this problem is to add fillets to smooth out the transition between the surfaces, making the velocity change more gradual, minimizing the turbulence and thus the drag. There are a few factors which significantly affect parasite drag. First, like lift or any other kind of drag, it will vary directly with the square of the indicated airspeed. If IAS is doubled, parasite drag is quadrupled, and if IAS is halved, parasite drag is reduced to a quarter of its previous value. Changes in configuration will also have an effect on parasite drag, which varies in direct proportion to the frontal area presented to the airflow. This cross-sectional area is known as parasite area. If flaps and landing gear are lowered, speed brakes extended, or roll control spoilers operated, parasite area, and thus parasite drag, will increase. Airframe contamination, that is, accumulations of ice, snow, frost, slush, mud, or even insects, will increase the parasite drag coefficient. In the case of severe airframe icing, the parasite area may be increased also. From this examination of parasite drag, we shall move on in the next lesson to the other main constituent of total drag, induced drag.